重哦。那你有不舒服吗？你两个不舒服吗？我不会想动，走一走它。这人想动。对，一天到晚都还没有动的。对啊，这我可以理解的。你不想动，动一下。这个一个别的，这个还。
我很快再看了一下那个图哈，就是原始式的那个，然后这里要讲的是，他把第一个他考虑大部分程式语言是 row major 所以他把第一个 index 一样的放在一起，还是这些内容，他把它改成这样零的只有00要处理，一的有1011要处理，以此类推。所以程式变这样，所以这个是它的，这个是把上面那个程式改成比较适合 row major 执行的。好，那最后谈的是这个另外一个做法，就是如果你还是习惯这一种，那这种的话就必须把所有的阵列，你看第一个 index 跟第二个 index 交换。那为什么会需要这个就调整这个？就是这里如果是整个程式计算最多的地方的话，其实是有必要为这个改一下 array 的编排好，但是这个讨论最主要是让我们知道说，平行计算的效能跟这个 data 的位置是有关系的所以这方面的考量称为 locality optimization。那这里面的考量你又分两件事，第一个叫 data reuse。这个也就是如果这个 data 用到后面还会再用到的话，我们尽量让这一个 data 第一次用跟下一次用时间越靠近越好。也就是不要在 loop 前面用到 loop 后面用到，为什么？因为前面用到这个 data 的时候会被载入到 cache， 中间如果你经过很多不同的计算的话，那个 cache line 可能会被 refresh 掉，你下次用又是从 memory 读进来，这样子的话，其实在 data reuse 的话，它的效能并不好，尽量让趁着这个 data 在后面写的 the same cache line 都放在 cache 里的时候，我们把它要用的 reuse 的统统处理完，这个是考虑 data reuse 的情形。第二个叫 data dependence， 也就是如果资料跟资料之间有这个dependence 的关系的话，要把它分析清楚。那如果你在平行化分工的时候，这个我们把分工的方法写出来，也是一种 loop transformation 针对 locality 做的 loop transformation 的时候，你要保证转换之后的正确性好，那这里一个例子，就是把 我们先看这个 assignment，z 的第3i 加5个 element 的 value copy 到7i 加3。所以 i 等于0的时候，就是第5个 value 卡到第3个 ；i 等于1的时候，是第8个 value 卡到第10个。看起来是不会有重复吗？会不会？好像会哈。第17加21i 的地方，它就有一个重复的位置哈。我的注解的第一行是3i 加5，第二行是7i 加3。所以loop 第一次的时候是第5个卡到第3个，第8个卡到第10个，第11个卡到第17个，第14个卡到第24，然后这个17是卡到31。重点是这个31是 depend on 这个第17个，但是第17个的执行必须在第3个 iteration 执行完。这个 dependence 的关系在做 locality optimization 的时候就要分析进去。好，那讲到 data reuse， 其实在 data reuse 的分析里面有第一个叫 self reuse， 也就是用的是同一个，通常指的是同一个 array element。好，那第二种叫做 group reuse， 就是某一个计算用到3个 operand， 然后 assign 到第4个东西的话，它第一次会出现在第一个argument， 第二次出现在第二个 argument， 第三次出现在第3个 argument， 第4次出现在被 assign 值，以此类推哈，也就是它是不是同一个 index 同一个 loop iteration 同一个 statement 用到的那这种分析起来就会更复杂一点点哈。同一个 element， 它在不同时间被用到，这个问题称为 temporal， 不同时间用到的。那另外一个问题是 spatial， 也就是它被用到的时候，我们尽可能趁着它在 cache line 里面，把它的几次用到的时候都把它用完，也就是这个 cache line 被 refresh 掉，换另外一组资料放到 cache 的时候，那我们它一旦被 refresh 掉，我们就其实不再需要它，这样会达到最高的提升效能，执行效能。也就是它一旦被载入 cache line， 我们尽可能把它所有跟它相关的计算都计算完。这种问题称为 spatial reuse。好，那课本11.5也就是讲这个 data reuse 的部分，还有很多考量我只把最重要的几个重点挑出来。好，然后这个我发现一直忘了标它是课本哪边我该下课的时候看了一下，是11.6然后11章我忘了查它有几个 session， 好像有到10几个 session 所以你可以发现每个 session 我都只挑重点稍微讲一下而已但是实际上每一个 session 都有大概3到6个 subsection 所以其实如果这个地方要仔细讨论的话，要花非常多时间好，最后我们时间关系，我们只讲到11.6 array 的 data dependence。重点是，其实跟前面谈到的有一点点关联类似这个案例这个 case 这里有用到，对不对？这里有一个 dependence， 那我们要怎么解决这个 dependence 的问题？ finding whether there exist integers that satisfy a system consists of equality and inequality。也就是我们在这个 loop 用到哪几个 index 的这个条件比较大小的，是否相等或者是否不等，或者大于等于小于等于都算在内哈。好，我们怎么样在最快的时间找到它的 integer 整数解，然后看这个整数之间是不是有关联？所以课本有给一个完整的 data dependence analysis algorithm。好，我只把重点摘要一下，好，详细的算法请你查一下课本。好，他把演算法分作3段，第一段，这些 index 的 linear 的条件有没有 rational 解，也就是会有解，会不会有解irrational 就简单讲，就是在整数的世界里找不到这个符合这些条件的 index。有第一个，如果有合理的解，那第二个，快速的用整数带进去，看能不能找到合理的整数解。好，那这两种条件符合的时候是比较容易找到的，比较快，用简单的方法。那如果前2个找不到的时候，我们并不能证明没有解好，那这个有一个真的去把所有解找出来的演算法，叫你常看到这位数学家，他想了很多这一类的问题，Fourier还有 Motzkin 2位提出来的一个解这种很多维空间里这个线性不等式的这个找到合乎这些条件的解，他们用的方法叫做 Fourier-Motzkin elimination。它的 loop 每一个 iteration 会先处理一个维度啦，所以如果这个是7维空间，它每一个 iteration 处理掉一个维度，你那 loop 要 loop 7次就可以找到有没有符合这些条件的解。好，那对于这个，其实坦白讲，如果是我在学生时代看到这种，我都很好奇怎么解的那有兴趣的人自己去看这个解答好，课本有这个 Fourier-Motzkin elimination algorithm。好，那今天的小考题是这一个，其实是一个简单题目我把这个课本题目把它变简单一点点把 index 变小。所以是课本11.3.2习题的简化版。那这个 loop i 1到小于10，所以是1到9然后 i 加2到20减 i， 然后把这个 xij 设成0，那到底哪几个 array element 被设成0的 iteration space 画出来？那忘记什么叫 iteration space 的我刚才下课加了进去就是画这样这张图 ，i 跟 j 它是几到几，把这张图画出来。当然这张图是 i 是0到5，j 是 i 到7，都是小于等于的比较。那我们这里小考习题好像不是小于等于是小于的比较。好，所以自己稍微注意这个差别，然后把 i 跟 j 在2维空间整数解的位置画出来。好，有没有问题？没有问题开始做英文的 summary。Okay, time for English summary. Okay, let's use maybe you already noticed I stayed on this slide for a very long time. Basically, I know the possibility is very low, or only very rare case that one of you would be interested. I emphasize that if you are interested in a PhD degree, and especially the interest comes from your intention to find a faculty job in college, then I would say compiler is a very good research area for such students, because almost every school, the computer science department requires at least one of the faculty members to teach programming language and compilers. In other words, all the university with computer science department will be your target for sending your resume. If you're working on a very hot topic or a new topic for your PhD degree, then it depends. Not all the department, computer science department in all university would like to hire a new faculty member for a new topic necessarily. And if you're going to work on compiler for your PhD research, this topic, the topic for this week, for this lecture, will be a very good possible area for you to find a research topic as a PhD dissertation. Because to my knowledge, not all the algorithms in parallelism is very mature. When I say mature, I mean if you try your best to find a better algorithm for sorting, then I would say sorting is already mature, and don't waste your time finding a better algorithm for sorting. And for parallelism, that's not the case. I mean, still I believe there are a lot of algorithms in this topic may have room for improvement. So it's a very good topic for doing PhD research. So first thing is, if you're interested in a PhD degree, and the reason is for finding a faculty job, then I would say compilers, especially parallelism, is a very good target for selecting PhD research topic. Okay, that's why I spend so much time here when I do Chinese lecture. Okay. The target for parallelism research is the scientific engineering or commercial, or I should say huge commercial applications have an insatiable need of computational cycles. I can use another term for this. In other words, we are interested in the computation-intensive software. Since it's computation-intensive, if we run the program with a single-thread CPU, and all the other optimization already applied, and you write the program with very good skill, then you leave our last hope in reducing execution time. That's by parallelism. If you cannot do one job in one day by a person, then one of the solutions is you hire more employees. You have 2 persons to get it done in one day. It's similar to this case. If we cannot improve the execution time by one CPU, and then we try to find the possibility to reduce execution time with multiple CPU. And when we try to do the parallelism analysis, we need to make sure the program has minimized communication among the process that are distributed to different CPU. And we need to do data locality analysis to make sure we can take advantage of parallel machines. And here are the 2 hardware architectures for research on parallelism. The first one is called multiprocessor architecture. The key point is that all the CPU share a large memory space. And that's the case in hardware. We have a motherboard that allow we set up multiple CPU on the board. And usually they have a universal shared memory space. And the second kind of the environment is like this. Every CPU has its own memory space, and they are not shared. And actually, you can think of this case as that we use internet to connect multiple computer systems. And the memory is on each of the computer systems. And they are put together by wiring, then together with a bus or with an internet. And the speed up of parallelism actually is a little bit related to the solution of our previous exercise, quiz exercise. If f is a fraction of all the code, a fraction of the code may be parallelized, and we have p processing. Then this part, the execution time of this part can be done by f over p. And the other parts cannot be parallelized, then the execution time is still the same as single-threaded environment. So the total execution time for parallel environment is this formula at the bottom, and the number you get is some number less than 1, and it's revert. So speeder is a number more than 1, larger than 1. Okay, in the beginning, or there is a very hot area for parallelism research called SPND. The same program run by multiple CPUs, and they operate on multiple data. One of the example is this one, the code on the left. The loop body, the first statement assigns x of I minus y of I and store the result as z of I. And the second statement computes the square of z of I. And the key point here is that the i's iteration has nothing to do with the other iterations. It does not depend on the other iterations. And that's the case that's the candidate for us to do loop, or I should say iteration distribution. We can have different CPU work on different iterations, and each iteration is distributed to one of the CPU, and the CPU can operate on each iteration. This is the case that for iteration distribution, if the CPU gets the cell number B, and we know that each CPU need to operate on P iterations. So if you get the cell number B, you are responsible for iteration B times P to, actually that's B times P plus 1 minus 1. That's of your duty. That's your responsibility. You need to work on these iterations. Okay, then that's the motivation for the topic of iteration space. Because when we talk about control flow of loops, we can distribute iterations to different processes. There is another consideration so that in order to make the most benefit of parallelism, that's the consideration of data locality, especially the data required by the iteration. That's called iteration space. If we have a nested loop, the outer loop iterate on I for the case I is greater n equal to 0 and I less than n equal to 5. And the inner loop on J has the condition greater than or equal to I and less than or equal to 7. So on the two-dimensional space, you can draw the numbers that satisfy the two constraints from that's 0 to 5. and j I to 7. That's how we call iteration space for the two constraints. And the key point here, not only we need to consider the dependence between iterations and the iteration space of data locality, and there is another precondition that we can benefit of parallelism. That's no execution order between iterations. In other words, the indices of the loop, we can distribute the iterations to different processes, and there is no time dependence among the iteration distributed. In other words, we don't need to wait for some iteration done first before we may start this iteration. Here is a case for dependence. There is an example here. In the loop body, we assign the value z3i plus 5 to z7i plus 3. This line shows the indices of 3i plus 5. So first iteration we have 5. Second iteration is 8, 11, 14, 17. And this line shows the indices of 7i plus 3. So first iteration is 3 and 10, 17. So here is the point. So this iteration depends on this, I should say, this iteration depends on this one. Oh, in other words, the third iteration needs to be computed, finish computation before the fifth iteration may get started. That's data dependence. In data locality, this shows the consideration of data locality. The loop is on the top right corner, and on the left hand side, the figure A shows each row shows an iteration of I. So when I is equal to 0, we use Z00, Z10 to Z70. And there is an error in this figure is a screenshot of the textbook. This one is wrong. It's 7-1 instead of 1-7 here.
And Professor, the original axis, the order should this specific belongs to the bottom order, right? Not the top one, the bottom. For this one, the original or the A, it's that bottom, right?
No, the original is this one. But if we change this into this one, we might get better performance. That's before we consider the performance, we need to know that the arrangement of array elements. Most of the programming languages support row major order of two-dimensional arrays. In other words, for a two-dimensional array 3 by 3, we number each element 1, 1, 2, 3, 3, and we make each cell a distinct number 1, 2, 3, 4, 5, 6, 7, 8, 9. By row measure, the elements are arranged in this way: 1, 2, 3, and 4 following 3, and so on. However, there are some programming languages support column major order two-dimensional array. The most famous one would be Fortran. Fortran is column major. But that's all for our traditional Fortran. I believe the modern Fortran changed. It's something like Fortran 95 or Fortran 2007, something like that. But column major order, the cell is ranged according to the blue or green line here. In other words, in the memory space, the A11 is here, A21 is here, and then A31, then A12, 22, 32, and so on. So the column major, the memory space is arranged in this order. So, as you can see, this loop is good for column major programming languages. If you are working with a row major programming language like C, Java, Ada, Pascal, then it is suggested that we change the loop into this so that we may we may operate on the array in this order, 0, 0, 1, 1, 0, then 1, 1, because they are consecutive. And in the third iteration, we operate those on Z2 and 3 and so on. But that's for row major. Don't run this on a column major programming language. Okay. And there are two types of data reuse when we consider data locality. The first one is called self-reuse. Usually it's the same statement in a loop, and we will go to the loop for more than once. That's self-reuse. The other case is called group reuse. If a statement has operates on more than one, for example, 3 array elements, and when you go to the detail, looking at the indices, say A of k, in one iteration is the first argument, and the other iteration it may be the second argument, and the third iteration is the third argument. Then that's group reuse. Consider the case of reuse. Is the first thing is called temporal. Temporal means the time that we operate on the data. And there is another consideration called spatial. It's that we try to keep all the operation on the same data as close to each other as possible, because we want to make it possible to keep the data in the same cache line as possible. If they are in if our second use to the data when it's still in the cache line, we can get the value more quickly. I mean, compare with to read the data from main memory. So that's called spatial consideration of data reuse. For data dependence, we have data dependence algorithm introduced in our textbook. And the algorithm has 3 parts. The first one is analyze on the conditions and check whether there are rational solutions. If there are, then we try to get the integer solution as quick as possible, because usually in the loop indices we only need integer solutions. But if we need other solutions as well, then we need to use the full algorithm to compute for the numbers in satisfy the constraints. That's full Moore-Skin elimination algorithm, which produce a polyhedron with one field dimension in each iteration. So when we apply this algorithm, in each iteration we reduce the number of dimensions by 1, and then after we finish the loop, we can get the solution. That's all. The exercise is reduced from textbook exercise. Actually, I make the numbers smaller for you to easier to draw the figure. Show the iteration space of this loop. You may slide 11. When we say iteration space, we need you to draw a figure like this one. Okay, but the constraints are different in our quiz exercise. Okay, that's all for today's lecture. Any questions? Okay. Yeah, you have a question. No.
No.
Okay.
So when we apply the constraints on these specific constraints, we get the flow.
Okay.
So these are switches, right? Let's see how this looks like.
Yeah.
Okay.
But actually, I wish you can draw the dots on the figure.
I kind of got lazy.
Okay.
I just drew the area. Yeah. Yeah, I put dots there, but it's hard to plot on this.
I mean, it's okay from this quiz.
Okay.
If in our final exam there is such a question,
then
remember to
put the dots.
Yeah.
Okay.
Okay, okay. 我也知道我们课本的习惯就是重则化 A，横则化 C。不过反过来没有关系，没有人会一定哪一个重则哪一个横则。 最近是不是推甄结果都出来了？这一届台清交的多吗？不知道。我们好像有几届清大、交大去蛮多的，台大通常一届一两个，但清大、交大有时候有几届会蛮多人的。
我就不要丢下来，这个